Hi everyone, my name is Barak Hadad. I'm here with my teammate Zusman, and we are about to show you how we use the Urgent 11 vulnerabilities to exploit Rockwell and Schneider PLCs. Another teammate, Gal Kaufman, also helped a lot with this research. He's probably at the beach right now, thinking about the next thing he's going to exploit. We are the research arm of ARMIS. We research unmanageable devices, generally devices that you can't put an agent on. We look for threats and anomalies in the wild and look for vulnerabilities in widely used devices. A quick recap about Urgent 11. These are 11 critical vulnerabilities that we disclosed in Black Hat USA 2019. They affect hundreds of millions of devices, and industrial control systems are also affected, including Rockwell Automation, Schneider Electric, and Siemens devices. We will start this talk with a quick overview of the operation technology, OT, world and the OT security concerns and standards. Then, we will show how we used one of Urgent 11 vulnerabilities to get remote code execution over Rockwell and Schneider PLCs. The main concern in the OT environment is the physical safety aspect. These devices monitor chemical and physical operations, so the main concern of the OT operator is that nothing blows up and everyone and everything is safe. From that aspect arises everything else. That's why the network is usually very reliable, with backup topologies in place. It's common to see network rings so that everything functions properly, even if some part of the network disconnects. PLC, Programmable Logic Controller. This is the brain of the factory line. And to keep the safety standards high, these devices are heavily tested and monitored so that they almost never crash or reboot. It's enforced from the OS level and up. Most PLCs use some type of real-time operating system as the underlying OS. One of those is VxWorks, which we will talk about later on. Comparing PLC to a Raspberry Pi, they have the same functionality, but the PLC do so in a much more reliable way. That's also why PLCs cost 100 times more than a Raspberry Pi. We can divide the OT network into 3 sections. The corporate network, that's the normal IT network with databases, PCs, printers, and things like that. Then we have the SCADA network, supervisory control and data acquisition. These are the devices that should monitor the production network, including the engineering workstation, the station from which the PLC is being programmed, and the historian server, a server that monitors the PLCs for regular checks and operation reviews. And then, last, we have the production network. It consists of everything you can find on the assembly line. PLCs, sensors, actuators, things like heat sensors or DC motors. Purdue. The Purdue model is used as a concept model for ICS network structure. It is an industry-adopted reference model that shows the connections and dependencies of all the main components of a typical industrial control system. The security standard in the OT world relies on Purdue model. It divides the devices into levels and states that each level should interact only with the levels above and below it. The model is just a logical representation, and in reality, everything is usually connected to the same switches and the same network. Sometimes even the same network as the IT network. The whole purpose of the OT network is the control and monitoring of the PLC. Since the PLC is at the bottom of the information flow, it tends to be the target of OT attacks. 2 known OT attacks are Stuxnet and Triton. Stuxnet is a malicious computer worm first uncovered in 2010, thought to have been in development since at least 2005. Stuxnet is believed to be responsible for causing substantial damage to the nuclear program in Iran. Triton malware was first discovered at the Saudi Arabian petrochemical plant in 2017. Both of these attacks began by taking control over the engineering workstation, which is a Windows machine, and from there injecting code to the PLC so that the attacker can execute unmonitored commands without the operator ever knowing about it. Okay, a bit more about the PLC. You can program the PLC, but in a safe way. Not every command is legal, and there are no interfaces to the underlying operating system. Also, every bit of data used by the PLC program can be monitored from the engineering workstation. Using a malware, an attacker can covertly change the PLC program just like Stuxnet and Triton did. Then he needs to hide himself somehow. Hiding the malicious operation can be done at level 2 by injecting all of the monitoring devices, or from level 1 by injecting the PLC that is controlling the operation and altering the PLC outgoing messages. Full control over the PLC code, even the non-programmable part, is not trivial. Schneider PLCs will prevent execution of unsigned programs, and Rockwell PLCs emulate the code and do not allow native code execution. Okay, so that's how a PLC actually looks like. On the left, we have the control logics, a PLC by Rockwell, and on the right, we have the Modicon PLC by Schneider. Both of these PLCs are made out of swappable slots. Each slot has one specific functionality, like I/O, networking, or the actual computation unit. When we first got the devices, we looked for some debug interface for easy exploration. Actually, since the connection to the engineering workstation is done via the networking module of these PLCs, our research focuses on getting control only over this specific module. With full control over this module, an attacker can alter the PLC program while showing the real engineering workstation a false view of the current PLC state. We opened both of the PLCs up, both of the networking modules, looking for some hidden serial, JTAG, or some hidden crash dump interface. On the left is the Rockwell network module, and on the right is the Schneider network module. We soldered in JTAG connections and SD card connections, but it all failed. We could actually see the SD card clock working properly, but nothing was being written into it. Next, we looked for all TVEs and found that the debugger was once open in the Rockwell PLCs. We downgraded the device, but it still didn't respond to any debug requests. So we opened the old firmware of the Rockwell PLC and found the debugger Easter egg. This function is the initialization function of the debugger. By setting the PLC IP to that secret IP, we could communicate with the debugger. The debugger gave us the ability to read, write, and execute arbitrary code. So we now have the proper tools to develop the Urgent 11 exploit. I'm going to pass the presentation to Dor, who will talk about the Urgent 11 vulnerability we are about to exploit.
Okay, so to get a debugger, we need to quickly recap a previous publication of ours, Urgent 11. So what is Urgent 11? Urgent 11 are 11 vulnerabilities that affect an operating system called VxWorks by a company named Wind River. If you're interested in more in-depth look on those, go see our Black Hat talk at 2019 Black Hat USA. It's important to say that Barak's hidden debugger is the OS default VxWorks default debugger, which is compiled into the firmware. So first thing first, why did we even do Urgent 11? We at Armis believe that shedding a light on a hidden attack surface is much better than hardening an existing one. After all, there are many talented researchers that look at Windows or Linux. Just as an example, Windows had 357 CVEs on Mitre for 2019, and VxWorks had only 13 CVEs ever before we added another 11 with our research. So there's a really big research gap there. So let's go back to what is VxWorks. I'm going to do a really quick recap of Urgent 11 and the vulnerabilities. So VxWorks is a real-time operating system owned by Wind River and used by more than 2,000 device manufacturers that need a reliable and compact operating system. Real-time operating systems excel at being compact and reliable and can deliver deterministic timing for various tasks. These features usually fit well with various embedded devices, and as Barak previously mentioned, the OT industry likes it to use exactly that. VxWorks is the most popular real-time operating system, and it runs over 2 billion devices, the same number of devices that are actually powered by Android or Windows, so a pretty large amount of devices. But unlike Android or Windows, this OS suffers from a lack of research. In its 32 years of existence, only 13 CVEs were listed, as I mentioned, until we added another 11 and jumped that number to 24. In comparison, Android has over than 2,000 CVEs in existence, and it exists about a quarter of the time. So now that I have convinced you that VxWorks is a pretty big research gap, I will now talk about where is VxWorks and where is it used. VxWorks is indeed in almost every industry, in healthcare, aerospace, and etc., and obviously in manufacturing. Basically, if you're a vendor who is in need of a reliable, standardized, and embedded real-time operating system, VxWorks will likely be your go-to tool. And in fact, you can see that the largest companies in their field uses VxWorks in their in their devices. You can see here a lot of really big names such as Rockwell Automation, Siemens, Alcatel, and so on and so forth. Schneider Electric, a lot of really big vendors use VxWorks, and even NASA uses VxWorks to power its previous Mars rover, the Curiosity. So what is Urgent 11? It's 11 vulnerabilities in the IP stack of VxWorks, which is basically a different component inside of the system that is responsible for the networking of the device. We have 6 remote code execution and 5 information leaks, denial of services, and logical flaws that in the context of OT and manufacturing, denial of service is almost as bad as remote code execution for obvious reasons. So during our disclosure process, we encountered a really big problem because the vulnerabilities that we found was inside of the Interpeak IP stack inside of VxWorks. And actually, this IP stack that was developed by Interpeak was acquired, the whole company was acquired by Wind River in 2007. But unfortunately, Interpeak had different customers before it was acquired. So it sold its IP stack to Integrity OS, Nucleus OS, the schematic on the bottom you can see is Itron, Inea OSE. All of those operating systems have some version of them that has the vulnerable IP stack and thus are vulnerable to Urgent 11 vulnerabilities. And once we tried to patch and fix all of this, we found that actually vendors buy an operating system, puts it in a device, and inside this operating system, there is the vulnerable IP stack. So basically, you have a supply chain inside your supply chain, which makes patches incredibly hard and mitigation even worse. So now that we talked about all that, enough of the high-level stuff, let's go back to the bits. So remember that Barak mentions that a PLC has a magic IP that he binds to and activates a debugger. So let's talk about one of the logical flaws that we found, which is the reverse ARP one, the ARP. So what is reverse ARP? Basically, we all seen this diagram, this network diagram. You see an ARP request, a client asking the network, who has that IP, I am that IP, and the device should answer. So reverse ARP works like this. A device sends to another device on the network, hey device, this is your IP, and VxWorks by default responds by okay, thanks, which is kind of weird. It's actually a state confusion inside of the machine that manages the reverse ARP, and most of the modern devices doesn't even support this. So on to the next vulnerability. You can imagine we can use that one to activate all of the hidden debug features and so on and so forth. And the next one is a bit more interesting. It's the IP options overflow. So to talk about that, we're going to need to talk about what is IP options. IP options is basically a way to extend the IP protocol, and it's obviously implemented inside of the IP header. The IP header has a field of the IP options, and it consists of an array of a type length value fields that every option has a unique type. It specifies the length, and inside the value, it can specify its own data structure. This time, we're going to focus on a specific IP option, which is the strict source and record routing, the SSRR one. This option basically lets the sender specify the route in which the packet must go through in order to reach its destination, and router must accept that. Just by saying that, you can already imagine the security implications of it, and that's why it's a common practice to ignore such an IP options, but VxWorks supports this to some degree, as we will see. So this is basically the route data inside of the SSRR option. Basically, it's an array of IP addresses that the packet must bounce through, and a pointer which points to the current IP address. The actual usage of it would look something like that. A client first composes the route data of all the routers he wants the packet to go through. It sends the packets to the first hop and sets the last hop to be the destination. It sets the pointer to the first of the route data, and then it sends the packet. The first router takes the pointer, advances it, changes the destination, and puts himself back in the route data list. This happens successively until we reach the final router who advances the pointer beyond the route data, and that way the destination knows he is the actual destination of the packet and not just a router on the way. Once he receives the packet and he wants to reply to it, he must respect the SSRR option even in the response, meaning you have to reverse the route data and send the packet in the reverse order. Okay, so far so good. But there is another mechanism in play here, which is the ICMP error one. ICMP errors are basically errors that can be triggered through a lot of network scenarios. I'm going to demonstrate, I think, one of the most common ones. A client sends data to a server on a port on which the server does not listen on, and the server receives the data, wants to inform the client that an error has occurred. What the server does is basically wraps the packet inside of an ICMP packet, specified the ICMP type to be an ICMP error, in this case port unreachable, and then sends the packet back to the client so he would know what packet caused the error. So far so good, but what if I tell you the erroneous packet came with an SSRR option within it? Should you now copy the route data back inside the ICMP error? And if so, what if the errors happened during the parsing of an IP option, specifically this SSRR one? Should you still copy the data? It seems not such a good idea. It's kind of tricky and not well defined. So let's just watch VxWorks' take on this. This is a simplified overview of the code flow that an IP packet takes inside of VxWorks' IP machine handling system. The first two steps validates and sanitizes the packet and delivers it to the layer 3 handlers. Basically, let's imagine an ICMP echo request arrives, then this machine will validate the packet, do all the route logic, and once the packet is validated and sanitized, it will deliver it to the ICMP handler, which in this case would generate an ICMP response, echo response. But VxWorks tried to be generic on this and use only one function to send ICMP packets. So the IPNet ICMP4 send function is called from different branches, even if it's a successful one, such as an echo response, or even a failing one, such as a param problem, which happens during the validation of the IP options. And how does this function handle being called from different branches? You guessed it, it does not. It just blindly tries to copy all of the IP options into the new packet, which can obviously cause an error if the options are malformed. Here you can see in the memcopy in the length field, you can specify a problematic length field which will fail the validation, but still will be called, this function will still be called and try to copy it. And also there's another flow here which you can specify only one IP option per packet, and it does not validate, there is no duplicate options. So basically you can specify a whole bunch of SSRR options with invalid length, and it will try and run this memcopy on every single one of them, which will cause a stack overflow inside of the IP stack. Okay, so now I'm going to transfer to Barak. Thank you.
We started out by checking that the vulnerability actually works. So we turned on the device, fired up the malicious packets with AAAA as the payload, and watched them crash. Here is the result. You can see on the screen that the device crashes on TNet0 task, which is the IPNet task, and the PC, the program counter, is 41414140, which means it's attacker control. It ends with 40 because jumping to an odd address in ARM architecture actually jumps to the even address and sets the mode to thumb. So yeah, we have full control over the program counter. Next, we wanted to find better crash messages. For the Rockwell PLC, we found a web interface with a lot of useful data. One of those is the assert log, which logs the crash messages, including the program counter and the error that caused the crash. For the Schneider PLC, we found that there is a command that you can send for reading the last crash message, including the registers. So now we have the ability to see what happens when the device crashes. Couple that with the debugger from the one day we've mentioned before, and the conditions are perfect for exploit development. After that, we looked at the binaries and found this data structure. Every record starts with this 50,000 hex, and then there are two addresses. When telling IDA these are offsets, we get this. So this is the symbol table, and now we have the names of most of the functions and also of many global variables. From the function names, we could conclude that some of the code was written in C++, while the operating system was written in C. And it all made one big happy binary. For the actual exploitation, we checked what mitigations we are up against. We found that there is NX bit, the code is write protected, and the stack is non-executable. But that's all. There is no ASLR or any other type of mitigation. That means that the code and stack locations are static. It eases the exploitation development a lot, because now we know that the memory layout is deterministic. There is no need for any type of info leak for the upcoming exploitation to work. We explored what primitives we can get out of the Urgent 11 IP options vulnerability, and we found that after all the byte juggling that the function does with the IP options, we have control over almost 7 D-words on the stack, and we can control which D-words these are going to be. Since the stack is non-executable, we figured that we will need to make a write what where out of this stack overflow and write our shellcode in chunks somewhere else. For that, we are going to use register 10 and register 11, hopefully finding a gadget that writes the data in one of them to the offset in the other one. We also overwrite a PC and 3 other D-words so that we can have a 4 D-word ROP return-oriented programming chain. In the table on the right, you can see the actual data in the stack when we sent an exploit with the A letter 41 in ASCII all over the buffer. As I said, we have full control over register 10, 11, the PC, and 3 other D-words, while registers 5 to 9 are filled with mostly uncontrolled data. So we found this gadget. It takes register 10 and writes it to register 11 plus 1 AC. So we just need to take the address we want to write to, subtract 1 AC, and put the value in register 11. After that, it zeroes out register 1 and register 0, adds 18x to the stack pointer, pops some registers, and returns. Now, we need to somehow restore the execution, so the device won't crash every time we trigger the vulnerability. Let's look at the epilogue of the upper function, the one that called the vulnerable IPNet ICMP4 send. It ends with a pop of register 10, 11, and PC. You can see that in the table on the right, the overflow overwrites the return address in the current stack frame, but the upper stack frame remains untouched. By using a gadget that will pop this untouched value from the upper frame, we can restore the normal flow of the code and prevent the device from crashing. We found these gadgets. The first one puts the value of register 11 in register 12, and the second one adds register 12 to the stack pointer and pops registers 6 to 11, and the PC, just like we wanted for execution restoration. When we set register 11 to 18x, the device doesn't crash. So we just need to take the write what where gadget from before and maybe add another gadget so that it also restores the upper frame. All we needed to add is just one pop and return gadget. And now we have a write what where exploit that doesn't crash the device, and we can use it to write our shellcode in chunks somewhere else. For the Rockwell PLC, we found a code cave that is writable, zeroed out, and executable. That means game over for the Rockwell PLC. We just write the shellcode and jump to that address. For the Schneider PLC, we needed an extra step. We used the write what where functionality to write an unconstrained drop chain that adds execute permissions to our shellcode, and from that point, it's the same as if it was with the Rockwell PLC. We merged everything together and wanted to make sure we have full control over these devices, so we decided we will try writing something to the 4-byte monitor of the Rockwell PLC. And yeah, after a lot of debugging, it worked. We were able to write to the device monitor while it was still functioning properly. Let's do something more complicated, or in other words, time for some demos. Okay, so as you can see, we control what's written to the device, and everything else is still green. So the PLC is still functioning normally and continues doing its normal task, while our task writes to the monitor of the device. For Schneider, we had a very similar exploitation. So there is no display on this PLC, so we used Morse code to send a distress signal using the PLC LEDs. So let's start the video. Okay, on the right you see the attacker terminal. And in a second you'll see on the top left the LEDs of the PLC, and on the bottom you see the packets that are being sent. And you can see that the LED signals SOS, so the PLC is trying to signal something out. The next demo is a broadcast attack. For this demo, we used the Rockwell PLC and a Schneider PLC on the top. The Rockwell PLC is connected to a PowerFlex motor controller, which connects to an actual motor. And we'll start this. OK, so you see the motor spinning, and you see the screens of both of the PLCs on the top left. OK, now we have a Wireshark view and the attacker view, sending one packet that will crash both of these devices. OK, the packet is sent. Both of the devices crash. And as you can see, the motor stopped working. Now, I want to mention that when this happens, the device doesn't reboot. So it will not work properly until someone physically comes to these PLCs and reboots them physically. You can't do this from afar. So this kind of attack can be devastating for an actual plant of some sort. OK, so another demo. This is a motor attack. In this demo, there is a Rockwell PLC on the bottom right, connected to a PowerFlex motor controller, which connects to a motor. We removed the Schneider PLC. This time, we'll show how, like Stuxnet, we gained control over the actual movement of the motor without the engineer ever knowing anything about it. So in the bottom right, you see the engineering workstation view with a monitor of the actual motor. And the blinking LEDs show that the engineering workstation actually monitors the device. Then we have the attacker view on top of that. And in the top, we have the view of the packets that are being sent. This time, we need to upload a big chunks of code because this code does a lot of stuff. So when it finishes uploading the code, it will turn the motor in reverse. So instead of spinning to the clockwise, it will spin counterclockwise. After that, the attacker sets the speed of the motor to the max speed. All of that being done while the engineering workstation knows nothing about it. It still receives the same messages as if everything is working correct. So you can see the motor spinning not as it's supposed to do. And in the end, the attacker sets back the speed and the direction of the motor to the original one and leaves it as it was. So the engineer working with the engineering workstation knows nothing about the attack that just happened. Okay, you can see now it spins back as it was, and the engineer knows nothing about it. Okay. So, a few more things to consider. Even a denial of service can take down a factory. These devices don't turn back on automatically after they reboot, and an operator needs to manually go and activate the PLCs one by one when they crash. Also, it's hard to patch these devices. It requires a production shutdown, and that rarely happens. And last, 7 D-words is way too much when exploiting ARM32 bits. We needed just 5 D-words, and we urged the viewers to make an exploit with even less. Thanks a lot. We're releasing a sequel white paper with the data from this presentation on the Urgent 11 page, and now time for some questions.